On the night of August 15, 1977, a radio telescope in Ohio recorded a narrow signal from the direction of Sagittarius. The signal lasted 72 seconds. It was strong enough to stand above the background noise. It sat close to the radio frequency emitted by neutral hydrogen. Astronomer Jerry Amon circled the printout and wrote one word in the margin. Wow. The signal never repeated. No telescope has confirmed its source. It remains unexplained, but unexplained does not mean alien. It is a useful starting point because it shows the standard that any claim must meet. A possible alien signal must survive instruments, interference, statistics, and time. The strongest evidence for alien life is not one mysterious event. It is a chain of scientific clues. Some clues are mathematical. Some come from planets around other stars. Some come from chemistry. Some come from searches for technology. None is proof. Together, they make the existence of life beyond Earth a serious scientific possibility. In 1961, radio astronomer Frank Drake wrote an equation for a meeting at Green Bank Observatory. The Drake equation was not a detector. It was a map of uncertainty. It estimated the number of civilizations in the Milky Way that might be able to communicate by radio. The equation begins with the rate at which stars form. It then asks, what fraction of stars have planets? It asks how many planets could support life. It asks how often life begins. It asks how often intelligence and technology follow. It ends with the lifetime of a communicating civilization. The early terms are now better measured than they were in Drake's time. The later terms remain mostly unknown. The equation matters because it separates evidence from assumption. A universe full of planets does not guarantee a universe full of civilizations. A single long-lived technological species would change the odds. A short technological lifetime would make contact rare. The Drake equation does not prove aliens exist. It shows where the strongest evidence must be found. For most of modern astronomy, planets around other stars were suspected but unseen. That changed in the 1990s. In 1992, astronomers reported planets orbiting a pulsar called PSR B 1257+12. In 1995, a planet was confirmed around the Sun-like star 51 Pegasi. Since then, thousands of exoplanets have been confirmed. The Kepler Space Telescope changed the scale of the problem. Kepler stared at a dense star field and watched for tiny dips in starlight. Those dips revealed planets crossing the faces of their stars. Kepler showed that planets are common in the Milky Way. Current surveys imply that many stars have planets. Some systems contain compact chains of worlds. Some contain giant planets close to their stars. Some contain rocky planets similar in size to Earth. The phrase habitable zone means a range of distance where liquid water could exist on a planet's surface. It does not mean a planet is inhabited. It does not even mean a planet is habitable in practice. Atmosphere, geology, magnetic fields, stellar radiation, and history all matter. Even with those cautions, the number's large. The Milky Way contains hundreds of billions of stars. If even a small fraction hosts temperate rocky planets, the galaxy could contain billions of possible laboratories for biology. That is one of the strongest pieces of evidence. It is not a sighting, it is scale. Life on Earth changed the air. Photosynthetic organisms filled the atmosphere with oxygen over geological time. Microbes and ecosystems also release methane, nitrous oxide, and other gases. A biosignature is a feature that may be easier to explain with life than without life. Oxygen by itself is not enough. Methane by itself is not enough. The most interesting cases involve combinations of gases that should react away unless something keeps replacing them. Earth's atmosphere is one example of chemical disequilibrium. Astronomers now try to read exoplanet atmospheres by studying starlight filtered through them. This method is called transmission spectroscopy. The James Webb Space Telescope has measured molecules in the atmospheres of some exoplanets. Most of those planets are large, hot, or unlike Earth. small rocky planets are harder targets. Claims about possible biosignatures remain cautious and disputed. A planet called K218b has been reported to show methane and carbon dioxide, with debated hints of other chemistry. Those observations do not prove biology. They may describe an ocean world, a gas-rich mini-Neptune, or something else. Inside the solar system, possible biosignatures have also produced arguments. A phosphine claim in the clouds of Venus was announced in 2020 and then challenged. Methane has been measured near the surface of Mars, but its source remains uncertain. At present, no accepted biosignature beyond Earth has been confirmed as life. The evidence is promising because the tools are real. The verdict is still absent. A technosignature is evidence of technology beyond Earth. It could be a narrow radio transmission, it could be a laser pulse, it could be waste heat from large-scale engineering, it could be artificial chemicals in an atmosphere, it could be a pattern that nature is unlikely to make. Radio remains the classic search method. Natural radio sources usually spread energy across broad ranges of frequency. A very narrow signal can suggest an engineered transmitter. That was the logic behind early SETI searches. In 1960, Project ʻOumuamua listened to Tau Ceti and Epsilon Eridani. It found no alien signal. Modern SETI is broader and more sensitive. Breakthrough. Listen began in 2015. It has searched nearby stars, parts of the galactic plane, and nearby galaxies. It has found many signals made by human technology. It has found no confirmed extraterrestrial transmitter. This absence matters, but it is not final. The search space is enormous. Frequency, sky position, timing, signal type, power, and duration all multiply the difficulty. Humanity has examined only a small fraction of the possible technosignature space. A failed search can rule out some kinds of transmitters nearby. It cannot rule out quiet civilizations, distant civilizations, brief signals, or technologies unlike ours. Unexplained observations are often treated as a separate category. They are not all equal. Some are instrumental errors. Some are ordinary objects seen under unusual conditions. Some remain genuinely puzzling. The WOW signal belongs in this category. It was interesting because it was narrow, strong, and close to a frequency valued in radio astronomy. It is weak as evidence because it was never seen again. Another case is Tabby's star, also known as KIC 846285-2. Kepler data showed deep, irregular dimming of this star. Some dimming events blocked more than 20% of its light. A few researchers and commentators considered artificial structures as one possible explanation. Further observations favored dust and natural material. The case became a lesson in restraint. A strange light curve is not a megastructure. In 2017, astronomers detected ʻOumuamua, the first known interstellar object passing through the solar system. It was elongated or flattened in shape, based on its changing brightness. It also showed a small acceleration not explained by gravity alone. Most researchers favor natural explanations involving unusual ices, fragments, or surface effects. A minority has argued that an artificial origin should be considered. The evidence does not require that conclusion. Military and civilian reports of unidentified aerial phenomena also remain in public debate. Some cases lack enough data for identification. Lack of identification is not evidence of extraterrestrial origin. The investigative rule is simple. Anomalies can guide research. They cannot substitute for confirmation. Proof would need more than surprise. A convincing radio-technosignature would repeat. It would be detected by independent observatories. It would come from a fixed astronomical direction. It would avoid known human interference. It might contain structure that carries information. A convincing laser signal would need the same independent checks. A convincing artifact would need physical recovery, traceable custody, and materials or engineering beyond known natural and human sources. A convincing biosignature would need a planetary context. It would need multiple gases, climate models, stellar data, and false positive tests. Even then, it would prove life more directly than intelligence. A fossil or microbe from Mars or an icy moon would be powerful evidence for a second origin of life if contamination could be ruled out. A second origin inside the solar system would change biology. It would imply that life can begin more than once in one planetary system. That would make life elsewhere more plausible. It would still not prove civilizations are common. Science rarely rests on one dramatic fact. It builds a case through repeated measurements. The strongest future evidence will probably be boring at first. It will be a spectrum, a signal log, a sample tube, or a repeated observation. Its power will come from surviving every attempt to explain it away. The strongest scientific case for aliens is cumulative. The galaxy contains immense numbers of stars. Planets are common around those stars. Rocky worlds exist. Chemistry can be studied across interstellar distances. Life appeared early in Earth's history, although the exact timing and pathway remain debated. Technology has emerged at least once. These facts make extraterrestrial life plausible. They do not make it established. The strongest counterweight is silence. No confirmed signal has arrived. No confirmed alien artifact has been recovered. No confirmed biosignature has been found. The silence may mean life is rare. It may mean intelligence is rare. It may mean technological phases are short. It may mean the galaxy is full of life that does not transmit in ways we can detect. The honest conclusion is narrow but profound. There is no scientific proof that aliens exist. There is strong scientific reason to search. The best evidence so far is not a single mystery in the sky. It is the discovery that Earth is one planet among many, orbiting one star among hundreds of billions, in a universe where the experiment has had many chances to run. That's why, Source. If this was worth your time, like it, share it, and tell me in the comments what you want examined next.